Okay, so we are talking about the chapter number 20, Infinity. And here we are discussing the different types of infinities. And we have started that two sets A and B are said to be equivalent to each other if there is a bijection from A to B. And we write this relation A related to B if A and B are equivalent to each other. And then we have said that this relation is an equivalence relation, and we have proved that. Then we have talked about the countable sets. So a set is said to be countable if A is equivalent to the natural numbers. In other words, A is countable if it is an infinite set, all of whose elements can be listed. So if you can list the elements of any set, then that set becomes countable, even though it is infinite. So then the union of any two countable sets is again countable, and every infinite subset of the natural numbers is also countable. Let's talk about that. Is Q countable? Yes, it is. Q is also countable, the set of rational numbers. And then now we are going to talk about the last point is the Cartesian product of any finite number of copies of natural numbers is also countable. Now we are going to talk about an uncountable set. So we have shown that many sets are countable. Are there in fact any infinite sets that are not countable? The answer is yes. So if we write that as a question, are there any infinite sets that are not countable? The answer is yes. There are sets which are not countable. And here is the most famous example of an uncountable set, where, not surprisingly, an uncountable set is defined to be an infinite set that is not countable. So let's give that as a theorem. (21.1). The theorem says the set of real numbers is uncountable. We will give the proof. So to prove that, we prove this theorem by contradiction. So suppose that R is countable. This means that we can list all the elements of R as a set which has R1, R2, R3, and so on. Now express each of Ri's in the list is a decimal. That means we can write R1 as M1 dot A1, A11, A12, A13, and so on. We can write R2 as M1, M2 point, A21, A22, A23, and so on, and R3, which is M3 point, A31, A32, A33, and so on. And this goes on up to Rn, which is Mn point, An1, An2, An3, and so on. And this also goes on, where each Mi is an integer and each Aij belongs to the set of positive integers. Aij is a set of positive integers up to n. Sorry, up to 9. Now define a real number. R as a decimal 0.B1, B2, B3, so on, as follows. To choose the first decimal digit, B1, if A11 is not 1, let B1 is 1, and if A11 is 1, let B1 is 2. That means hence A11 is not B1. Now to choose the second decimal, digit, B2, if A21, sorry, A22 is not 1, let B2 is 1, and if A22 is 1, let B2 is 2. So again, hence A22 is not B1, and so on. So in general, to choose the nth digit, decimal digit, Bn if Am is not 1, let Bn is 1, and if Am is 1, let Bn is 2, hence Am Nm, actually, not Am only, Nm is not Bn. So in this way, we define a real number R, which is 0.B1, B2, B3, so on. Now, since R1, R2, R3, so on, is a list of all real numbers, R must belong to this list. To this list. So R is Rn for some n. For some n. But Bn is not equals to Nm, Anm. So R and Rn differ in their nth decimal digit. Note also that R does not and in recurring nines or zeros means all the BIs are 1 or 2. Hence, R is not equals to Rn, which is a contradiction. Therefore, there is no bijection from naturals to reals, which is to say that R is uncountable. Very nice. And this proves the theorem. So we have just shown that the theorem 21.1, which says the set R of all real numbers is uncountable. Okay. Now this famous theorem is due to George Cantor. So we can write that with a bold ink. This is given by George Cantor, who is the founder of modern set theory. The wonderfully clever idea of the proof defining the decimal by adjusting the diagonally placed decimals a and m in the area of Ri is called Cantor's diagonal argument and can be used to prove that all sorts of other sets are uncountable. A consequence of this theorem is that a consequence of theorem 21.1 is that the set of rationals, which is R minus the rationals, is uncountable. And imagine if irrationals were countable, then the rationals would be the union of R and Q and irrationals, and that would make real numbers countable, which is not the case. So, for if it were countable, then R would be the union of two countable sets, and hence would be countable. Thus, there are in some sense more irrational numbers than there are rationals. Perfect. Now, if this is the case, then we should talk about which numbers are more and which numbers are less. And to talk about that, we need to talk about the hierarchy of infinities. And to explain that, let's talk about a topic, a hierarchy of infinities. And we will explain this by a definition. So definition is, let A and B be sets if A and B are equivalent to each other, i.e., there is a bijection from A to B, B, we say that A and B have same cardinality, and write order of A is order of B, right? Okay. Now, if there is a bijection, if there is a one-to-one function even, not a bijection, but a one-to-one function even from A to B, we say or we write that order of A is less than or equal to order of B. Okay. And if there is a one-to-one function from A to B, but no bijection from A to B, then we write that order of A is less than order of B, and say that A has smaller cardinality than B. Thus, order of A less than order of B is the same as saying that order of A is less than or equal to order of B, and order of A is not equals to order of B. Okay. Now, according to this definition, we have order of natural numbers is equal to order of rational numbers, which is also equals to the order of the Cartesian product of naturals and naturals, and the cardinality of n is less than the cardinality of real numbers. Thus, there are at least two different types of infinities, namely, thus, there are at least two different types of infinities, namely the order of naturals and the order of reals. Are there more types of infinities? The question is now, are there more types of infinities? For example, is there a set of greater cardinality than R? Is there a set of greater cardinality than R? Well, the answer is yes. And the answer first comes into the mind is complex numbers, but that is not the correct answer. So the answer is yes. Again, this is due to Cantor. Again, this is due to Cantor. To understand this, we need the definition. So let's give a definition now. So let's say we have a set. If S is a set and let we denote P of S by be the set of all the set consisting of all the subsets of the set S. For example, we know the examples a lot, and we count that if S is finite set of size n, then the order of the power set can be calculated by 2 power n. And this is a proposition 17.3. We have proved this proposition before, so go and check it out. Now, Cantor's theory is based on the following result. And let's give that result. We have a proposition 21.5, which says that let S be a set. then there is no bijection from the set S to the power set of S. Consequently, the order of the set S is less than the order of the power set of S. Okay. Now, using this proposition, the proposition we obtain a hierarchy of infinities starting at cardinality of natural numbers, and that is the cardinality of natural numbers is less than the cardinality of the power set of natural numbers, and it is less than not equal to the cardinality of power set, again the power set of natural numbers, and we go on to write more and so on. Thus, there are indeed many types of infinity. Okay, and we will end this chapter here. Will not give the proof for this one. It can be proved, but just know that this result, and that would be fine for you. Okay, perfect.